everybody for joining, being a part of this maybe wild ride today. Thanks for having me back from I think 1 or 2 years ago, and I think I will be able to manage it in half an hour, 25 minutes maybe. So today I will be talking, as it is Valentine's Day, about a very special lady in hopefully a very appropriate way and fashion, about Viking lady, a PSV, and an article I came across a few years ago, which has pretty much stuck in my mind and haunted and given me now the chance to have this presentation and maybe other stuff as an outlet of it. Start with some words up front as the last time. So this is, of course, my personal approach to the topic, is my conclusions based on the information that is available publicly, which I've used. So the conclusions you or others may make on this data and this presentation is, of course, all your own risk and fault. I have no connection to any of the companies and projects mentioned in this presentation. And if you are wondering about everything, want to give me some feedback, or you just need to press on this little head down here on every slide, and then you will Outlook will put out an email, and then you simply can write me an email. This might be of interest for the people, for the students which are writing their bachelor thesis right now and might have a question or two. So just plugging quickly, and that's the reason I pretty much this article has haunted me. We started a new master course, and as a part of this master course, I have a master program. Sorry, I have a course which is on maritime propulsion technologies, and this includes some of these topics, and some of these topics I will get into today, but as Elvis Costello said, sorry, ladies and gentlemen, there's no reason to talk about this right now. So we're talking about the article and what got me hooked. And I have, based on the feedback I got from IDESWIC, I have to make a correction, which is not directly visible on the title and screen for the article, about the world's most important ship who has been retired, because it hasn't retired. The ship is still in operation. Just the research project that has been done on this ship and the technologies that have been investigated. This research project has, of course, ended after, I think, roughly 10 years, 15 years, something like that. These are all the partners. This is the LNG tank that has been installed. This is the control part of the hybrid system. This is the control view of the molten carbonate fuel cell from MTU. And this is pretty much the layout of the ship, which has been used. On the left-hand side, you see the research project, Fellowship 1 and 2, which have looked at the installation of the natural gas fuel, diesel pilot fuel ignited engines. They took a look at the natural gas fuel molten carbonate fuel cell. There's not much said about this. That's why I won't be saying a lot more about it. And then in the third part of this project, they took a look at a hybrid system with a Corvus battery, roughly 0.5 megawatt-hour capacity. This ship has been the first LNG fuel PSV in 2003. It has been the first PSV which was allowed, or which could operate dynamic positioning in 2016 based on battery only. So this has made quite some significant leaps for technologies related to shipping, which have been applied and used on the ship quite a long time before. They're now getting more and more into the focus of the general interested populace, I would say. Not least, which I would briefly get back to later is there's, apart from the technological stuff, there's also a lot of rules and regulations which have been pushed forward. For example, the IGF code regulating low flashpoint fuels, which, for example, natural gas or hydrogen or ammonia would be. Ammonia is not technically a low flashpoint fuel, but it will be covered by this. Also, the DNV class society rules for dynamic positioning operation with batteries have all been largely influenced and been elaborated in the course of this project. So some results from the project using this neat little underwater picture of a bunch of happy people, because there are a lot of happy people involved with respect to the use of these technologies. You've got, of course, the crew, which is based, if you're looking at articles or presentations or information material, it's quite happy. If you're looking at their hybrid solution with a battery, it's of course using a battery makes the operation more silent. Maintenance of a battery is, I'm not quite sure if easy or simplified is the correct way to describe it. I would say it's simplified. Of course, might not be easier. And if the crew is happy, the captain is of course happy, especially if you have all the peak shaving, if you can be also with respect to dynamic positioning, transit of the vessel, if you have an increased responsiveness. In general, engineers, pretty much from a mere technology-wise, it's functional. Having a battery, it makes it much easier also for the engines, for the operation of the engines. I had to pick someone for the owner and operator, and I used the cashier, so I think it's maybe most appropriate. They are happy, even if it doesn't seem like that. Having reduced both the cost in general, the operational cost, which is that, and especially fuel and maintenance costs. And of course, for the financing people, it's low risk. Is what's low risk? It's very depending on where you are and what you're dealing with, but in general, it's lower risk financing a project with technology that can be used and is relevant and has short payback times based on the cost for the both natural gas and general current at that point in time. And finally, also the environmentally concerned people could be a little bit happier with such a solution, as of course it reduces the emissions. I try to keep it a little bit vague because emissions is quite a big topic, and what you consider emissions sound both above and below sea level is also emissions and is also important. And the battery itself does not, or if it's battery driven or engine driven, does not change the sound of a thruster or propeller under the water. This will be the same, but in general, it's better. It's a step forward. And if I remember the numbers correctly, I think the payback time at that point in time was 4 years or below for the system, and they had saved, I think, roughly $500,000. And you can, it's dollar or euro. It's not kronas per year on the fuel bill. Out. So if you look at the time, the fourth dimension, what has happened during this process, and just to keep a general view on the topic, the project started in 2003. The first proposal for a new regulation for IMO that would regulate low flashpoint fuel ships, in this case natural gas, was implemented from Norway in 2004. 5 years later, you had the interim guidelines. Another 6 years later, you had the code itself adopted, and another 2 years later, it entered into force. So 13 years have gone just to implement it, and then based mainly on natural gas, not even talking about hydrogen, ammonia, methanol, and other things like that. This year, from the beginning of this year, you have to have a regulation regarded to the energy efficiency of existing ships, EEXI, and the carbon intensity of your ship. So, and this will run on until 2030, where you should have a reduction by 40%, and 2050, where there's an X at the end, because IMO hasn't agreed yet on the level of decarbonization, 50%, 70%, 100%. And yeah, the EEDI, EEXI, all these energy efficiency measures have several parts. They have 3 parts. One for the ship management plan, one for the fuel oil consumption, which you have to report, and one for the carbon intensity of your operation, based on the ship size, the nautical miles you travel, and stuff like that. And if you take a look at a typical timeline for a ship, if you start this year with development and engineering, you start constructing next year, and you keep it in operation, so you end up in 2050 with what you're doing right now. And this is a little graphic I borrow from DNV about the carbon intensity. You have to be at sea level ideally. That's the thought, the carbon intensity, but you can have a D grade for 3 consecutive years, and then you have to do measures to start getting a C grade. And then, of course, you could, if you, yeah, I wouldn't call it smart, but of course you could move back. But this, in general, the intention for the carbon intensity is that you, at sooner or later stage, switch to a carbon neutral or carbon-free fuel. If you're taking a look at a more micro level for time, of course, for some of you it's surely known. I had to put a little bit of time in it, which I have to anyhow. It's the correlation between the power you need on board of the vessel and the vessel speed, and the safety margins, especially what you have to take into account from sea trial, from calm water, and from adverse conditions. And based on a report, based on the Sandia report, which I reference later, I took a look at some of the vessels. You see a very big container ship here, typical vessel and typical trip, intercontinental vessel from, I think it's from Singapore to the US, roughly 5,000 nautical miles. If it runs on the speed it's designed to run, it's roughly below 11 days. If you increase the speed by 2 days or decrease the speed by 2 days, you move faster or slower, more days. For some of the ships, it has a major impact. For some of them, it's not. And the problem is, of course, if you go down to the high-speed crafts, which are typically operating on a 15, 20, 30 minute schedule, on the bigger scale, it actually doesn't matter that much. And for the final version, just a note to myself, I need to correct this. Maybe the slide a little bit. And of course, what you have to keep in mind in addition, especially for the larger ships, based on the design of the ship, the hull, it might not make sense or might not be possible to increase the speed to a much higher level, because you will meet the so-called wave wall, where most of the energy that you put into the propulsion will just dissipate in wave energy and not actually be usable as a propulsion energy for the ship. So if we take a closer look, we stay at the Sandia report and the vessels there. We take a closer look at the type of vessels with their propulsion power and their typical energy consumption for a trip. Please be aware this is double logarithmic scale, so they can fit everything in one chart. You've got the intercontinental vessels, of course, quite high energy consumption and sometimes also high propulsion power. We've got the coastal cargo vessels, still quite high energy consumptions. We've got passenger cruise vessels. This could be a general cruise ship, which are high installed power, or just a smaller boat. We've got your ferries, you've got your offshore vessels, you've got your leisure and tourist crafts, got some fishing vessels where speed itself is not actually the issue. You don't think most of them will outrun the fish that they want to get. They just want to get the fish. And you have a different kind of energy consumption, of course, if you're based on what kind of fishing trawler you have. If you're just catching small amount of fish, or if you have all the refrigeration and all the processing on board of the ship. So this is just a closer look also at my watch at what shipping all encompasses, basically. And here we've got the Viking lady again, which wasn't part of the report, but just mention it. Then this 100 megawatt hours, this would include 50 hours of operation with a base load of roughly 500 to 800 kilowatts for some hours. Then you have a transit part going towards an installation. Then you have a long part, 20-30 hours of dynamic positioning, and then you transit back to your harbor. If we stay here and just take a look at the typical technologies used, you see for the larger vessels, it's slow speed, two-stroke engine at the moment running mainly on heavy fuel oil. The next envelope would be four-stroke medium-speed engines, and the smallest one, four-stroke high-speed engines. And in these areas, the gray and the red one, this is where we see some kind of change or conversion towards the solutions that have been presented or have been introduced, amongst others, by Viking lady, the PSV. We see a lot of hybrids. We see a lot of battery. We see conversion to cleaner fuels compared to heavy fuel oil with natural gas. And if you push it onwards with carbon-free or biofuels, both the area here and the distinguishing between speed classes is just again my conclusion, so to speak. So you can, of course, argue it would be 300, 250 revolutions per minute. It could go up to 15 or 1800. So that's not set in stone. This was quite a lot of work, and I don't want to spend a lot of time on it because it's hard to explain and it may confuse. But the general information behind this is we again have all the vessels. We have their typical tank volume. We have the different candidate fuels or energy carriers, for example, batteries. And you would see the typical trip distance with 5,000 nautical miles for the bigger one, and with the fuel capacity that they have. And this is the line 1, which would mean you could manage to do one trip on that kind of fuel. You see the batteries in all cases lies below 1. This is, of course, this is just an illustration. I spent more time on explaining right now than I should have. You can, of course, you can tune it. You can choose a different application. Battery technology has involved, so that's not the case. But what you see is that the fossil fuels mostly give you the best value, the highest amount of trips. Then you go down from LNG and methanol, you go to hydrogen, and you get a little bit up. And that's just explaining why you see maybe for the bigger ships an upturn and interest in ammonia. I'm not taking into account special additional space which you need to take into account if you go from liquid fossil fuel that you simply can have in the hull structure going over to minus 250 degrees insulated liquid and hydrogen tank. Well, just rounding up, staying with the time, let's see just what it would take for an LNG vessel which has LNG on board just to bunker. This has been made with all the steps, roughly 50 minutes to bunker 130 cubic meters. This is an example that I found from a Captain Numa on his very big container vessel. This is the time it took to bunker 10,000 cubic meters of LNG for the first time, from birth until unberth, over 50 hours. And the largest amount of time was taken to cool down the system before they actually could ramp up and start the pumping of the fuel. And this is based on LNG with rough tank temperatures of 154 degrees below zero. This might get smaller, might get bigger if you go to temperatures far below that. So at the end, this is a study done by DNV for the Port of Amsterdam, taking a look at an arbitrary number of hours. They said they think they will bunker, just need to take a quick look, it was 250 hours of LNG per year, just to have a number. And based on this 250 hours of LNG, they calculated with the available amount of technology and how much fuel you can push through a pipe, how many hours more or less they would use to transport the same amount of energy with a different kind of fuel. I put in a line, again, it's logarithmic, a line for the hours in a year. And you see that for most of the candidate fuels, you will have an increase. You will need twice the time. For hydrogen gas, compressed hydrogen gas, you have not that many hours in a year that you would to transport the same amount of energy across. So that's just for them to have an idea about what they would require on terminals and stuff like that. So rounding up, squaring the circle around the vessels. So you have a lot of different vessel types, and every vessel you have a different kind of parameters that you need to take a look at. Some weigh more, some weigh less for every vessel, but if you have to make a decision, you have to take a lot of things into account. And now I didn't look a lot at technologies, now I looked more around with respect to the infrastructure and the fuels. And if you want to just take the lesson learned for the project, that's quite simple. I'm not pronouncing it, I'm using the word upthrust. It's much easier for non-native speaker, at least for me. You will have a lot of factors in your equation to make your project float. And as far as I can see, and again, just a personal guess, I think for a lot of the innovative technologies, and it's being in the right place at the right time, which is highly important. If you don't have a vast amount or reservoir of natural gas, you might not have natural gas as ship fuel as your first idea on the list. That's I think valid for a lot of other technologies and energy carriers as well. So that's where I'm finishing above time again. Sorry for that. Not the 20 minutes, a little bit more based on my clock, but these are basically the literature I've used. I can highly recommend, of course, the Sandia report. If you have too much time on your hands, the roughly 500 pages of the IMO greenhouse gas study is surely a one that will bore you to death. Or the much older, but from Rolls-Royce Marine, the official available report about the application of fuel cells for surface ships from the year 2000 is surely worth taking a look at.